lattice energy is the change in energy when separated gaseous ions are packed together to form an ionic solid. Something in this form, a cation plus an anion, both in the gas phase, come together to form an ionic solid, and the change in energy is lattice energy. So with an energy diagram like this, which one of these would be the lattice energy? Sometimes this is a common mistake. Someone might say that this is the lattice energy. This is the overall net change. The lattice energy is something in this form. A cation plus an anion equals an ionic solid. So the lattice energy would be this last step right here. Lithium plus fluorine is equal to lithium fluoride solid, minus 1047 kilojoules per mole. And I guess I may as well go over the other steps out here while I'm here. Which of these would be an ionization energy? Ionization energy is giving up an electron, so it would be this one right here, lithium becoming a cation. So what about electron affinity? Electron affinity would be this one, fluorine accepting an electron, minus 328. But here's another interesting question from earlier in the class. Which one of these would be the rate limiting step? Well, the rate limiting step would be the step of the greatest energy, the greatest obstacle to overcome in order for this reaction to take place, and that would be the ionization energy of lithium. So this is an interesting observation of this reaction, because normally when people see very exothermic reactions, at least up to this point, they normally think of something that would happen. It's just like you put these two things together, it's just going to blow up, basically. But it's not the case at all. If I look at what is required, so let me just draw this out into an energy diagram. So let's say I've got just lithium and fluorine here. So actually the lattice energy part's over. I mean, lattice energy is pretty simple. It's just the energy released when the ions come together and become packed into a solid, and that's what this last step is. So this is just extra stuff that will lead up into later things that we'll learn later on, activation energy and things like that. I think we may have already learned some stuff about activation energy, but just in case, let's just go over this anyways, because it's interesting to see why certain things just don't happen spontaneously. You know, something that's pretty exothermic is when wood or something like that is burned. That's why a lot of heat comes off of it. But if I just throw wood and oxygen into a jar, what's going to happen? Nothing. So same thing with this. But let's have a look at why this is happening. So lithium plus fluorine, start here. And what's the first step? Okay, so first thing, 160. Actually, I should probably make this lower. Lithium solid plus, actually, this is technically correct. So first thing we're going to go up, it's going to take 161 kilojoules to get us gaseous lithium. So now we're going to be here. So I've got lithium gas. And the fluorine. So next what I need to do is ionize this thing. So this one's going to be 520. Next thing I need to do is divide or break this bond. That's 77. Now I've got lithium gas plus fluorine gas plus that electron. And now from here, this is an exothermic reaction. So this is going to start releasing energy. So now minus 328. So that'll put us somewhere around here. And what will we have? We'll have lithium. These are in the gas phase. And fluorine ion gas. And now here is the part with the lattice energy. So this is going to go down by 1,000 something. And then I'll be left with lithium fluoride solid. But look at why this doesn't happen just automatically. Here I've got, let's say this is the starting point here. I'm at 0. I've got to invest 161, 520, and 77. And it's not going to be until I get to this point all the way up here. So let me do this in a different color. All the way up here that this reaction is going to start taking place on its own. Once it gets up to this point where I've invested all of this energy, then from here on, then it's going to happen all by itself. But it's got to reach this energy first, so this is why it doesn't happen spontaneously, because a lot of energy needs to be invested in order to get it to go down. So the rate limiting step is going to be this one because it requires the most amount of energy. If I can get enough energy, this is going to be the step that's going to slow the reaction down the most because it's the greatest to overcome. So this was the rate limiting step, but still I need to, if I only had 520 and it was a solid still, then it still wouldn't be enough to go for this reaction to go, because I would still need more energy to break the fluorine bonds, and I would need more energy to break or to turn lithium from a solid to a gas. I thought I mixed these up here for a second, but no, I didn't. But this is basically what's going on. So it's important to know that although a lot of these lattice energies and oxidation reduction reactions are very, very exothermic, they don't necessarily happen spontaneously, or if they do, it happens very slowly. Think of a good example is, man, I like how this started as a lattice energy video, and then now it's a rate limiting problem, or whatever. Anyways, it's just think of like a newspaper. You know why newspapers turn yellow? It's basically slowly reacting with oxygen. If someone's ever thrown newspaper into a fire, it kind of turns yellow and then crinkles up and then turns black and into ash. But why newspaper is yellow is because it's slowly burning. That's basically what's going on. It's what happens when someone burns something is that they're reacting organic materials with oxygen. When I take paper, I'm reacting it with oxygen. That's all that's taking place. But the reason papers don't just burst into flame when I've got my book open or something like that is because there is this high activation energy. I've got to do all of these things before this can happen. Once I put this much energy in here, then the rest of it will happen on its own. So this is probably, I think this is later on where they talk about rates and different kinds of stuff like that, but it's interesting because there isn't really so much to comment on lattice energy. It's just the energy that is released when these ions come together, and really that just shows what a favorable state it is for it to exist in, rather as opposed to a covalent existence where they share the electron. The ionic bonds are more favorable for them because of this lattice energy. I mean, hopefully someone who just wanted the lattice energy hung in there until I said that, but I'm not going to remake this. This is just not, it's pretty self-explanatory.